Yeah. Hello, can you hear us?
Yes.
Okay.
Okay.
So you are all set?
Hence, now we just need to help presenters share your presentation.
Okay, you want να μου δώσετε τα αρχεία. Είναι όλα εδώ μέσα. Ο καθένας έχει το δικό του. Οπότε πάμε ένα-ένα. Ωραία. Πού πήγε το χάσαμε. Έλα εδώ. Βίζας, να τους.
Slides. Φόρτωσε το PDF, λέει presentation.
Το PDF.
Τελειώσαμε.
Control C. Θα βάλουμε εδώ επάνω στο desktop να τα έχουμε πρόχειρα.
Θα το βάλεις μικρό.
Έχουμε, το βάζω με τη σειρά, θα τα βάλω. Οπότε φεύγουμε από εδώ.
Αυτό φεύγει. Ήταν η τρίτη κατευθείαν.
Εντάξει, τα βάζουμε μετά με τη σειρά, λοιπόν. Eject. Πάει ο cruiser, έφυγε. Οπότε την βάζουμε λίγο πιο κάτω. Την τρίτη. Εδώ. Παίρνουμε ποιο? Το PDF. Το βάζουμε πρώτο, είπαμε αυτό. Πάνω. Είναι λίγο πιο πάνω, εντάξει. Eject. Πάει και αυτός. Η δεύτερη ποια είναι? Η δεύτερη ομιλία είναι αυτή. Το βάζουμε. Άρα, translate και παίρνουμε αυτό. Το βάζουμε δεύτερο. Πού πήγε? Έσπρωξε το άλλο λίγο πιο κάτω, μου φαίνεται. Εντάξει. Πάει και αυτό. Το βγάλουμε. Ωραία, πάει και αυτό. Άλλο. Έχουμε κι άλλο. Άλλο ένα. Άλλες δύο έχουμε.
Θα βάζεις με τη σειρά παρουσίαση.
Ναι, 1, 2, 3.
Ωραία, 1, 2, 3. Τώρα είναι το 4.
Τώρα είναι το 4.
Μανώλης Φιλάρδας και 5 ο Κουκουδάκης. Κάπου εδώ με τη σειρά.
Πιο κάτω. Ο pivot είναι αυτός. Ο pivot έκανε pivot. Ωραία. Πάει και αυτό. Και ο τελευταίος. Ωραία. Τι παίρνουμε τώρα?
Το στικάκι.
Συγγνώμη.
Είναι φάκελος presentation του σημερινού.
Αυτό, όχι Νάσκα.
IEEE
14-10.
Το PowerPoint, το PDF.
Το PDF και PowerPoint. Ή και τα δύο. Το PDF. Άρα το παίρνουμε έτσι, και το πάμε εδώ τελευταία. Ωραία. Τι παίρνουμε μια θέση πιο κάτω, δεν καταλαβαίνω. Έτσι λοιπόν. Πάει και αυτός. Θα ανοίγει τη σειρά.
Μπήκαν όλα.
Καλή επιτυχία.
Πρώτα θα δούμε ότι μπαίνει δουλεύει και μετά θα κάνουμε πράγματα.
Στο ανοίγουμε από εδώ.
Νίκο, πώς θα είμαστε σίγουροι ότι μας δουλεύει καλά?
Τώρα θα τους μιλήσουμε. Ακόμα δεν έχουμε κάνει share, μόλις ανοίξουμε το τέτοιο. Αυτό δεν το άνοιξε. Να το βάλουμε. Βασικά μπορούμε να τα ανοίξουμε και όλα. Full into full screen. Πρώτα share, κάνω. Share. Ωραία. Window αυτό. Ωραία. Τώρα full screen, πώς το κάνουμε. Δεν μας το φτιάξει. Από το Fuel θα το παίξει. Από το Fuel. Όχι, δεν μας κάνει. Όταν το θέλεις. Α, να το. Ήταν το F11 τελικά, αλλά δεν δούλεψε. Να ανοίξουμε και τα άλλα να είναι έτοιμο. Όχι, δεν χρειάζεται. Ναι. Έχουμε βγάλει το mute. Artem, can you see the...
Yes.
Yes, okay. Okay, so...
Πάει το επόμενο. Αυτό εδώ πάει το επόμενο slide. Α, πάει έτσι, με τα βελάκια, έτσι.
Hello, ladies and gentlemen. I would like to welcome you to this afternoon session entitled Mathematics of Data Science. We have 5 talks in this session, so I would like to ask the speakers to follow the limit time. The first speaker is Mr. Ioannis Jordanis. He's a graduate student in a master program entitled Mathematical Modeling in New Technologies and Financial Engineering. And his talk today is on regression analysis in machine learning using conditional latent hybrid sampling.
Hello everyone, good afternoon. My name is Ioannis Jordanis and I'm going to present a study with respect to regression analysis in machine learning using conditional latent hypercube sampling. This study was prepared by Professor Christos Koukouvinos, Iliana Silva and me. First, the motivation for this study will be presented together with a brief reference to related publications. We will describe the objectives of this assessment and the related publications and the methodology and the main results will be presented. Finally, we will conclude with the evaluation of the proposed method and suggestion for further elaboration. In our times, digital data is dominating in all domains. As you can see from the histogram, every year a huge increase in terabytes is recorded, and it looks like this increase of data volumes will be limitless. Data are generally available everywhere and in huge amounts, but the creation, collection, and elaboration of large databases may be extremely expensive and time-consuming. Therefore, the selection of those data, which can lead to the correct, less expensive and time-consuming conclusions is a pressing goal. Data selection as a sampling technique finds application in various domains in combination with machine learning, also known as ML techniques. So the aim of this selection is to reduce the sample size, but without reducing the volume of useful information represented in the sample. Latin hypercube sampling, called LHS, was recently proposed as a sampling method which provides full coverage of the variance of every variable by maximizing the stratification. This approach has already been investigated in some very interesting papers. Lee et al. Compared Latin hypercube sampling and single random sampling as per their ability to enhance the modeling speed of neural networks used in the fabrication of thin films. Minanci and McBratney in 2006 introduced an algorithm of intelligent sampling called conditional LHS or just CLHS. Yang et al. At 2020 integrated CLHS with machine learning algorithms to investigate the impact of sample randomness on soil mapping accuracy. And during our recent study of 2022, combining CLHS with ML algorithms, we found that using CLHS for dividing datasets into train and test sets in different machine learning models is an effective approach. The aim of this study is the examination of the response of advanced sampling mechanisms used in state-of-the-art machine learning processes. We implement the concept of intelligent sampling by applying CLHS technique in regression problems. We compare two data sampling methods, RS and CLHS. The comparison is made by applying machine learning algorithms and using open source datasets. These two sampling techniques are compared in the same metric in order to properly evaluate their performance. Let's say a few words about the datasets. The IRIS dataset consists of 3 classes, 50 instance seeds, where each class refers to a type of iris plant. 4 characteristics were measured: the length and the width of the sepals and the petals. The aim of this study is to predict the iris sepal length. Fish dataset contains information about the species, weight, length, height, and width of 158 data points. In this study, the aim is to predict the fish's width. And the vehicle dataset consists of 301 vehicles with information regarding several parameters, such as model, year, sale price, showroom price, etc. And in this study, we predicted the vehicle's selling price. We applied these algorithms on our data sets. And these algorithms are some of the most commonly used models in machine learning for regression analysis. The sampling methods used for the selection of the trained set are RS, where the sample is selected randomly, and LHS. In LHS method, for a data set of k variables, the range of each variable is split into n equally probable spaces, and then a random sample for each variable is taken for each space. The final sample is built from these n values taken from each of the k variables. These data points cover all n spaces for all variables, preserving the Latin hypercube properties. For the selection of sample points, we use the CLHS algorithm of Minanci and McBratney. Now, the steps we followed. First, we encoded the categorical values of each dataset into numerical values. Then each dataset was split into 80% train and 20% test datasets using the two sampling methods, RS and CLHS. Then for CLHS, the train set is further reduced in train sets 65%, 50%, and 40% in order to test CLHS performance using fewer training data points. In the next step, we applied the before mentioned ML models to perform regression, and the performance was assessed using the same training dataset every time by comparing the two the result of R-squared metric. In order to visualize the data points and to demonstrate how LHS techniques enhance the property of space filling, 10 points were extracted from each dataset using RS and LHS. You observe in IRIS dataset that the selected data points when using RS have very poor space filling, while using CLHS, we see that it is a better option in terms of space filling. Same goes for FISH dataset and vehicle dataset. Here is the evaluation of the IRIS dataset. The evaluation matrices for all machine learning models used for each dataset are presented in the following tables per train dataset size. The circles of the same color highlight the comparison between RS and LHS. For example, for the IRIS dataset, when we use CVR as an ML technique, with the red circle, all R-squared metrics achieved by LHS are much higher than with RS. And the higher performance is shown in 80% sampling. In a regression tree algorithm with the yellow circle, the result is again in favor of LHS, with the higher performance to be achieved at 65% sample. And as we can see in the tables presented here for the IRIS dataset, CLHS proved better training abilities in all cases, even with smaller sample size than RS. In the FISH case, the results were less satisfying. Nevertheless, using the two popular algorithms of CVR and regression tree, better predictions were achieved even with smaller samples, only 40%. In the case of vehicle dataset, again, CLHS resulted in more successful training in most of the supervised machine learning algorithms. For these cases, R-squared of LHS is higher than the respective RS for all sample sizes. Here we see collectively the models that demonstrated significant improvement in terms of the evaluation metric R-squared for all these datasets. In IRIS dataset, with the green color here, the CVR model of the same percentage, the metric increases from 85% to 89%, but the improvement with LHS occurs with smaller sample sizes, with smaller sizes as well. In these cases, in all models, the metric with LHS is higher than with RS. The same is noticed for FIS and vehicle datasets. And here we see the importance of good sampling, where data covers more space, even with smaller number of sampling points. Finally, in the next 3 slides, regression plots are presented in order to present the deviation between the predicted and actual values. The selected model for visualization for each dataset is the one whose improvement due to the use of CLHS is the greatest. At the right plot for IRIS dataset, we can see that the adaptation of data is better with LHS. The same applies for the other 2 datasets. The data are better adjusted, and the plots shown in a graphic way that the regression model is, gets improved when applied sample extracted by LHS. These are the FIS, the data from FIS dataset, and this is from vehicle dataset. So, in conclusion, it was found out that the CLHS significantly improves the performance of the regression model and often is the optimal sampling method. It should be noted that in some instances, when using CLHS, the performance of the model is equivalent or even greater with significantly smaller samples. Overall, CLHS, when combined with machine learning, can turn the algorithm to be more effective. So it is a useful tool for improving the efficacy of machine learning algorithms. In the future, the contribution of LHS technique is in unsupervised learning tasks, such as clustering and dimensionality reduction, and it should be investigated. Here we close our presentation. Thank you for your attention. Any questions?
Is there any comment or question from the audience? Also online, please check. Θα check it online. Νίκο, πώς το τσεκάρουμε?
Do we have any questions here?
Hello?
No.
Is there any comment or question? No. Okay, we thank again the speaker. The next speaker is Dr. Angeliki Lapa from National Technical University of Athens, and she's going to talk on variable selection in modeling with supersaturated designs, a comparative study. Angeliki, είναι μέσα το αρχείο.
Ναι, το άλεξα. Το κάναμε αυτό το
Έκανε save.
Δεν το κάνω.
Το βγάλεις το share.
Θα με τα δούμε. Α, όχι, είναι ακόμα. Ωραία, εντάξει.
Έκανα share το πλήθο.
Hello everyone, my name is Angeliki Lapa. Today we're going to talk about variable selection in modeling with supersaturated designs. This is joint work with Professors Christos Kokouvenos and Marilena Mitrouli. First of all, I would like to thank the organizing committee of DESSERT for this opportunity to be here. So let's see the contents of the talk. First of all, we're going to say some things about supersaturated designs and the linear regression model, along with the cumulative sum control result, which is a very powerful tool of statistical process control. Next, we're going to talk about some variable selection methods like SIS method and SIS-PURSUIT method. We're going to present our experimental results along with some examples and finally the conclusions and the references. Supersaturated designs appeal greatly to both scientists and engineers. They are designs with P factors with n runs, where n is less than P. They first appeared in Sutter White, and since then there has been a huge research regarding the construction and the analysis of SSDs. A comprehensive review can be seen in a year review in 2014. The analysis relies upon the construction, the assumption of effect sparsity, where we can say that only few factors are significant. The main goal of the screening experiment is to correctly identify the active factors while the inactive ones will be discarded. During the screening experiments, we consider the null hypothesis as 0 versus the alternative hypothesis. SIS-PURSUIT method that we're going to see later more extensively takes the active factors via the Kusuma chart in SSDs, assuming normally distributed response. Constitutes of two stages, where in the first we apply a raw screening procedure using SIS method, and then we apply the Kusuma chart in order to identify the active features. During the evaluation of a proposed method, like this, we evaluate the following criteria. Type 1 error, which is the cost of declaring an inactive factor to be active, where we reject the null hypothesis, and type 2 error, which is the cost of declaring an active factor to be inactive. Both of them must be kept as low as possible. Furthermore, in SSDs, controlling type 2 error, along with keeping statistical power as high as possible, is more critical than controlling type 1 error. Let's see the linear regression model that is given in equation 1, where y is our response vector, x is the design matrix, and beta is the vector of unknown coefficients, and epsilon is the random vector, assuming normality. Our goal in the screening experiments is to identify the non-zero effects, assuming there are up to m active factors from the total P involved. This is very important during screening experiments. First of all, let's see the cumulative sum control charts, which is a very powerful tool, as we already said, in SPC, statistical process control, and that will first appear by Page in 1945, 54, sorry, and where it's important because it detects very small shifts in the process parameters. For example, this chart is used for individual observations, and when the process is in control, we say that xi follows normal distribution with mi-zero mean and sigma standard deviation. The upper and lower Kusum statistics are given by equations 2 and 3, and C0 plus and C0 minus are the starting values that we used these cases for later during the SIS-PURSUIT method. K is the reference value, and we say that if Ci plus or Ci minus is greater than H with the decision interval, then its process is out of control. Note that both the decision interval and the reference value depends on the H and K lower cases. These values are very important in the PURSUIT track because they provide a chart with a good performance. For more information about the choice of these values, we refer to Montgomery. Let's talk first about Sur-independent screening, which is proposed by Fanelib in 2008. It's a raw screening procedure that uses the property of Sur screening. It's a variable screening procedure which selects the important effects with probability tending to 1. What this method does, it takes a truth sparse model, and with descending ordering through marginal correlation, produces a submodel where it produces a smaller model with size D, which is less than N. This method, we used it along with Kusum chart in order in 2018 in Rosso et al. And proposed cis-Kusum method. This method, as we already said, is combined with the previous cis procedure, and we test the factorial effects in supersaturated designs. It's described as follows. Using X, which is the SSD matrix, and Y is the normally distributed response, we compute the least squares estimators using the cis method from 1 to M, where M is less than P. And this can happen because M is less than N, since we choose active factor up to the half of the range. Then we calculate the absolute effects of beta I, and using the absolute effects, we can calculate then the upper statistic CI plus. In order to calculate CI plus statistic of the Kusum chart, first we set the standard deviation of the effects equal to the square root of the standard error of the linear model that we already know it. And then using KH according to Montgomery, we calculate the decision interval and the reference value. Given all these parameters, we say that if the CI plus statistic is greater than 8, then we can say that this factor is important active one. Otherwise, we can say that this factor is inactive, and we can further investigate the other factors. Note that we only use the upper statistics since we use only the absolute estimates of the during this procedure, since the CI minus statistics of the Kusum chart will always be equal to 0. Furthermore, we use the starting value different from 0 because according to our simulations, we have better results. According to these simulations and in respect to type errors, we show that the formula given equation 4 produces better results, where you can see it depends on the number of runs, the number of predictors, and the number of active factors. During our simulations, we use several SSDs, supersaturated designs, with different sizes, proposed by Kokovinos et al., Marlene Woods, and Tanke Wu. We compared the several variable selection procedures are cis-Kusum, cis, standard stepwise variable selection, and dancing selector that proposed by Foa et al. During our simulation procedure, we performed 1,000 simulations for each model, where the response was generated according to the linear model, and the SSD was the design matrix, and the error were normally distributed with 0 mean and unit variance. The number of active factors were ranged from 1 to the 1/2 of the runs, and the beta coefficients were generated from normal distribution for the active ones, and the inactive ones were set equal to 0. The Kusum parameters were set K according to Montgomery to K equals to 1.5 and H to 1.61. And during this procedure, we calculated type 1, type 2, as well as statistical power. According to our results, cis-Kusum improves the performance of cis. It keeps type 2 errors as low as cis. It reduces type 2 error up to 20%. And furthermore, comparing cis-Kusum with stepwise regression NDS, we can see that produces low type 1 and type 2 errors up to 1/3 of the runs. The type 1 errors of cis-Kusum for all the considered modes is lower than 10%. Type 2 errors are lower than type 1 errors for active factors up to 1/2 of the runs. And as for statistical power, cis-Kusum produces better results compared to the other methods and for all the considered models that we used. Next, we present the first example in our talk, where it's about the production of immediate release ciprofloxacin tablets, and it was presented in McGrath et al. In 2023. The design that we see in our slide, it's about 12 runs, is the rows. and 11 factors that were studied, and multiple response variables were analyzed, Y1, Y2, Y3, and Y4, as you can see in that slide. McGrath et al., as well as we considered two procedures. During one-stage procedure, we selected the terms in the model all at once. First, we assume that we have all main effects and two-factor interactions. So we have 11 main effects that presented in the previous slide, along with the two-factor interactions, which were 55. And during two-stage procedure, first, we selected only the main effects that were important, and then all two-factor interactions that made the weak or the strong heredity added to the model, and then we selected the final model. Note that when we say weak heredity, we mean that if the model includes A-B interaction, at least one of A or B factors is selected, also included in the model. If we say that we have strong heredity, it means that if the model includes A and B interaction, it includes A and B as well. McGrath et al. Performed during one-stage procedure SCAD-C, thus SCAD along with CI criteria, and during two-stage procedures, they performed SCAD-C, ball correlation-based Cs, and length test along with SCAD-C. During the one-stage procedure, we performed Cs, while in two-stage procedure, we performed Cs consumed twice. McGrath et al. And we performed our methods individually for each Y. So, for example, during the first Y1, we see that performance cut C in one-stage procedure, McGrath et al. Found that F is an active factor. It's an active factor. Cis consumed shows that F and IK are active ones, while during two-stage procedure, we can see that performance cut C twice, D and F are active. Big correlation along with SCAD-C shows that DEF, AE, BF, and EF are actives. Performing length along with SCAD-C shows that D and F are active ones, and performing Cis consumed twice, we see that DF and DF interaction are active as well. In the next example that was presented in Grosso et al. As well, we consider a very well-known dataset in SSD analysis, where it's a Williams rubber dataset, which proposed by Williams in 1968, where we have 14 runs and 24 factors. Note that the 13 factor and the 16 factor are identical, so one of them was deleted. So we have 23 factors. And the last column is the response vector. Performing the Cis-Kusum method, here we can see the chart Kusum that was presented in this slide was the chart that we constructed. We can see that the 14 and 16 factors are important in our experiment, and this is very important and significant because other methods as well show that the 14 and 16 factors are important as well. Finally, we can say that SSD analysis is a challenging area of research. Especially Cis-Kusum is a very important method because it keeps type 1 and type 2 errors as low as possible. The statistical power comparing to the previous existing methods produces very good results. And according to the real data examples that we saw, we can say that we can recommend it for variable selection and modeling SSDs. Finally, a serial procedure using Kusum can be performed assuming binary distributed response, and we can say that the further research can be done in multiple response analysis. Thank you.
Thank you, Judith. Is there any comment or question? From the audience or online, please check.
Do we
Hello?
have any questions online?
Is there any question? No. Thank you, Angelique, again. The next speaker is Professor Marilena Mitruli from National and Kapodistrian University of Athens.
Να τα βελιά και πηγαίνει αυτό, πέρα το επόμενο.
Okay. Marilena is well known for her significant contribution in numerical analysis and computational statistics, in particular in numerical linear algebra and regularization techniques. And she will speak today a fast, stable formula estimating matrix inverse.
Hello. This work that I'm going to present is in collaboration with a master student of National and Kapodistrian University of Athens. But even before starting, I would like to thank the organizing committee for giving me the opportunity to present this talk today, and also to give my warmest congratulations for the whole organization, which is really very nice, and give us the opportunity to meet all together and discuss useful scientific topics. So my talk concerns, I'm going to present you a fast and stable formula which can estimate matrix inverses, and especially can estimate the diagonal of a matrix inverse, which is a procedure which applies, and we can have it in many applications. Quadratic form of this type, x transpose A to minus Q x, for a matrix, for a square matrix A, arise in many applications, in statistics, network analysis, numerical analysis, and by choosing in this quadratic form the vector x to be vectors of the identity matrix, for example, epsilon I, with I only with one only in the I position, we can specify columns of the matrix inverse. So, which is the important idea here? The important idea here is that the evaluation, a direct evaluation of a matrix inverse, we all know that is an expensive procedure, is of cube cost, and the matrix inverse is needed in various applications. So, the idea is, can we replace an exact computation with an approximation one? And instead of having an exact formula, to have an approximate formula which estimates the matrix inverse. And especially, we are very much interested for the diagonal of a matrix inverse, which appears in several applications. For example, in network analysis, in statistics, we need mostly the diagonal of a matrix inverse. So let us see what can we do in case that we can have an estimation of the quadratic form. We can easily move into a bilinear form following to the polarization identity. So here are some related references. A lot of people in numerical analysis have worked in how can we specify an approximation of the matrix inverse. And there are several approaches. Some of them are based in Gaussian quadrature. Other of them are based in extrapolation techniques as the last reference, or other ones are based on global Lagrange decomposition. What I'm going to present here today is, let's say, a heuristic approach, which is the simplest one and gives us very nice formulas for this estimation. So let us start. We suppose that we have a symmetric positive definite matrix. This is a very nice mathematical property, if the matrix is symmetric and positive definite. And what is really nice is that in most applications, in real data, the matrix appears to be symmetric and positive definite, which is very good and for the mathematical task. So let us have such a matrix. Let us have a vector x, and the purpose of this work is to find an easy, fast, and stable estimation formula. Actually, we will have a direct formula, which we will show that it will be fast and stable. Let us see how we can produce this heuristic estimate. The main idea was, if we just study the very well-known Cauchy-Schwarz inequality, which adds to this very nice inequality, we can pick up this quantity and define it as index of proximity for a given symmetric positive definite matrix and for a given non-zero vector. just define this quantity, which, as we can see, only includes inner products and matrix vector products, and define it as index of proximity. From consist function equality, we know that is larger or equal to 1, and we can see here, according to this lemma, that for any positive definite matrix and any vector x, we can define this index of proximity, defined, you can see, according to the vector x and the given matrix. This is always greater or equal to 1 and becomes 1 only if, even only if he happens to be eigenvector of matrix A. Let us see now how we can proceed. This nice index of proximity has also these properties, which are equivalent if the index of proximity is 1. Also, it will be 1 for this matrix functional and general for this. This gives us the idea that we can continue in this way. Can we express the quadratic form as a function of this index of proximity? In this proposition, we can prove that this quadratic form is equal with this. It involves this index of proximity. So the idea of the heuristic approach is, can we find an estimation of this index of proximity and thus to have estimation of the quadratic form? So what we thought about it was that this index of proximity that contains a complicated matrix functional can be replaced by such a product which will be exact, the approximation will be exact if he happens to be an eigenvector, and according to the values of ki and pi that we can choose, which of course can be integers and arbitrarily selected, we can find an elegant formula. For example, if we specify that we want to keep here 4 pairs, Pk equal to 4, and give these pairs of values, k1, p1, this value, k2, p2, this value, easy and low values of them, we can derive this very nice formula which estimates the quadratic form. By making the appropriate replacements, we can see that this formula can be estimated by this one, which only contains matrix vector products and inner products, and will be known as estimation formula. Estimation formula. So, by also using this this equality, that this inner product actually is equal to the one on the right hand side, we can make some replacements to this previous formula. This is the initial estimation formula, and can be written in this equivalent way, which we rename it as modified estimation formula, meaning EF, which is written in a form that we can directly see that contains some inner products and matrix vector products, which, as we know, that in any numerical linear algebra computation, the MVP, matrix vector product, and the inner product are the basic units for any calculation. They are executed rapidly, and this, let's say, something very nice, because in the complexity it will be kept in a quadratic form. So, as we can see here, the complexity of this nice formula, actually this one that I presented here, which estimates this quadratic form, and again I must emphasize that for vector x, if vector x can be chosen as epsilon I, columns of the identity matrix, we can directly estimate entries of the inverse or the whole diagonal for every I. So the complexity is very low whenever we want to apply numerically a mathematical formula. Two things we must take into consideration. First of all is the complexity. So the complexity is very good. It is squared, not cubed as it is in the matrix vector. So it is fast because the complexity is good. And the second point, it has to do with the stability. It's a point that many times they don't consider it in a numerical calculation, and it is very important, the stability, because we must show that the computed formula is a slight variation of the theoretical one. It is very important, so if we can follow the Wilkinson's formulas about how error analysis in the mathematical formula can be performed, we can finally have, actually this is the algorithm according to which the formula will be computed. It is written here analytically. We can see that only has inner products and matrix vector products. And by analyzing all these steps according to Wilkinson's formulas for error analysis, we can have this very nice result for the stability, which says that if we perform it in fixed point computation or in floating point, according to the arithmetic computer, the result, the computed result, the fixed point on the floating point in a relative manner, that is the computed value, actually will be a variation of the theoretical one. This is the theoretical one, multiplied by 1 plus an error, and this error is well bounded. We can express a very nice bound as a function of n to this power, which is very satisfactory. This establishes the stability, that the computed result, slight variation of the theoretical one. And it is important such an analysis to be involved in any numerical computation. Let us also see now the behavior of the data to this formula. In this example, we test the covariance matrices. We compute the whole diagonal of the inverse of a covariance matrix. Up to the case we started of order matrices of order up to 10K. Here we can see the mean relative error. I must specify here that in most of the applications, statistics, networks, we are not so much interested for a very low mean relative error. For example, a relative error of 10 to minus 3 is very satisfactory. We don't want to move further, and we can see here that the behavior of this estimation formula is very good. It gives us 10 to minus 3 relative error, which is very much satisfactory. Also here, other covariance matrices of difference variables that can be defined. Again, the behavior is very nice. But what is important is that these heuristic formulas can behave also well for any random matrix. So we tested a random matrices, random in a random process, of this dimension. Again, the relative error, let's say, is acceptable. Is less, it is 10 to minus 1. And also we can see here, and some time in seconds, that even with this size of matrices, the execution time is satisfactory. And here the matrices are random SPD matrices. In applications that we have matrices of specific structure, the behavior is even better. So, what I can say in conclusion for all this approach is that we have fast, stable estimates for these quadratic forms, and thus and for the matrix inverse. And the basic idea is very important, that the data showed that they can be processed heuristically. And the trend that now, let's say, is dominant in machine learning is to learn from the data which is the appropriate numerical method that we can use for their, let's say, process and their execution in problems. So we think that these heuristic estimates can be satisfactory and also can be generalized. And for other powers, for example, not only minus 1, we are working now for estimation to 8 minus n for several, or by using other recursive sequence, and generally use heuristic estimates for many other processes. Here are some related references. Also, the trend of machine learning, as I told you, the recent book of Silverstrand, linear algebra, and learning from data. So study the data and according to them, adjust the procedure that we can apply for their process. And thank you very much for your attention.
there any comment or question?
Can you also please speak with symbolic emphasis?
Yes, I think it can be adjusted. Yes, yes, I think that it can be adjusted because the formula is simple. I thought that instead of reading the numerical value, can use a parameter. Maybe we can do it. Yes. Something else, maybe?
From online?
Okay.
Do we
Let
have
us
any
see.
questions online?
Okay, thank you again.
Sorry. From online?
No, it's okay.
No other question?
Hope it was okay and for the time.
Thank you again.
I spoke a little bit more rapidly. Thank you again.
The next speaker is Emmanuel Lardas from National and Kapodistrian University of Athens. Will talk on pivot patterns of Adamar matrices of order 20.
Hello, good afternoon. First of all, I would like to thank the organizing committee for having me. Today I will talk to you about pivot patterns of Adamar matrix of order 20. First of all, what we wanted to do in this work was to identify the possible pivot patterns that can emerge when we apply Gaussian elimination with complete pivoting to an Adamar matrix of order 20. We used a computational approach and we wanted to discover as many of these pivot patterns as we could by randomly generating Adamar matrices from ones that we already knew, applying GCP to them, and recording their pivot patterns. Some background, I assume you're all generally familiar with Gaussian elimination, so I won't go into much detail. It is, of course, a very widely used algorithm used in multiple applications. There is a major unresolved issue regarding the algorithm, and specifically concerning its stability. If we allow row swaps in partial pivoting or row and column swaps in complete pivoting, in order to ensure that the pivot at each step has the largest possible absolute value in the remaining submatrix, either within its own column for partial pivoting or within the entire remaining submatrix for complete pivoting, we get the algorithms GEPP and GECP respectively. In this work, we're interested in GECP. And the reason for this interest is that in the backward error analysis of GECP, the growth factor of the matrix to which it is applied arises as a quantity of interest. And of course, finding a relatively low upper bound for this quantity would imply that GECP is not just stable in practice, but also theoretically stable. So let's begin with some basic concepts. If we denote AK, the matrix that results from A after having performed k-1 steps of GECP, then for k up to n-1, the kth pivot is the maximum of all the absolute values of the bottom right submatrix of AK, starting at the kth row and column of AK. And the final pivot is the absolute value of the bottom right element of the final matrix. Then the growth factor of the matrix A can be defined as the maximum of its pivots divided by the first pivot, which is the absolute value, the maximum absolute value of any element of A. And since in the definition of the growth factor, the pivots appear, this means that the pivots and the pivot pattern itself, which is the sequence of pivots, basically, also arise as quantities of interest. Also, I would like to note that whenever we use the term pivot in this work, we mean its absolute value. I'm supposed to be talking about Adamar matrices. So what is an Adamar matrix? An Adamar matrix of order n is a square matrix of order n, with all its entries equal to plus or minus 1, such that when we multiply it with its transpose, the result is n times the identity matrix of order n. An Adamar matrix can only have orders 1, 2, or a multiple of 4, although we don't actually know if an Adamar matrix exists for each of these orders. It has been conjectured that the growth factor of any matrix is at most, of any square matrix, is at most equal to its order, with equality if and only if the matrix is an Adamar matrix. The inequality has been proven false in exact arithmetic by modifying the counterexample that did not account for rounding errors. But whether or not the second part is true, whether or not all LMR matrices have growth factors equal to their orders, is still unknown. It remains an open problem. We know that it does hold for small orders, specifically up to order 16. For 1, it is trivial. For 2, 4, and 8, it was proven by Day and Peterson in 1998. For 12, it was proven by Edelman and Mascarenas in 1995. And most recently, it was proven for order 16 in 2009 by Kavaridis and Professor Mitrouli. And in this work, what we're doing is we wanted to propose some algorithms that can be used to randomly generate LMR matrices of any order really, but specifically order 20, from ones that we already know, and compute their pivot patterns to find new pivot patterns. This can be useful as a guide for more theoretical results, as was the case for order 16, where all the 34 possible pivot patterns were discovered computationally before a theoretical proof was given. Now, in the algorithms, we're using some auxiliary functions and one method of vectors. I won't go into much detail. We can generally get the sum of all the elements of the given collection, vector, matrix, or set. We can choose randomly one element or any number of elements that we want, randomly and uniformly, from a given finite set of vector. We can append an element to a vector. We can count how many times an element appears in a vector. We can construct a vector of any length, a zero vector of any length, and a zero matrix of any dimensions. We can get the length of the vector and the size of the matrix in both dimensions together or each one separately. We can construct a vector by starting at a given number A, moving at increments of B, and going on until right before we surpass a given number C. And if we omit the step, it is assumed to be 1. We can get the ith element of a given vector V. And if for I we give a vector instead of a number, we get the corresponding subvector. And similarly for matrices, we can get an element of a matrix or a subvector of any of its rows or columns, or any submatrix of the matrix. Now, onto the more theoretical aspect of this work. Two or more matrices of the same order are called equivalent if we can get one from the other after a finite number of row swaps, column swaps, row negations, and column negations. This gives an equivalence relation, and the following table shows how many classes exist for some small orders. Unfortunately, equivalent NMR matrices may have different pivot patterns, which means that simply finding the pivot pattern of one representative from each class is not sufficient. However, we can use this to our advantage in order to find more pivot patterns by generating other NMR matrices from ones that we already know and computing their pivot patterns. This algorithm generates a set of information that can be used to describe such a transformation. It chooses a number of operations to perform, from 1 to 200 in this case. Then it chooses for each operation of which type it will be, counts how many operations of each type will perform, and then for each operation, for example, for row swaps, we choose which rows to swap randomly again. Similarly for column swaps, and then it chooses which rows and columns to negate and returns the information. Now, if we have such a transformation description and a given matrix, then we want to be able to transform the matrix, which we do using this algorithm. It goes through all the operations and simply performs the necessary changes depending on the type of the operation. This is how we do row swaps, and then column swaps and row and column negations respectively. And finally, we return the matrix. To find the pivots of the matrix, we can apply Gaussian elimination with complete pivot into the matrix and keep the absolute values of the elements that appear in the diagonal. Again, I won't go into any detail about how we're doing this. And finally, we return the pivots. Now, our next algorithm can be used to find pivot patterns. We construct a matrix that contains the ones we may have already found as its rows, and then It also constructs a vector that counts how many times each pivot pattern has appeared, and then it generates such a transformation as described before. It transforms each of the chosen representatives that we have in the list R according to that transformation, and finds the pivots of the transformed matrix. It checks if they're new. If they're not, it simply increases the count of how many times they have appeared. If they are new, it adds them as a row to the matrix N, appends the count 1 to the end of the vector counts, and stores all the relevant information. Counts is stored regardless of whether or not the pivot patterns are new. The pivot pattern is new. And finally, we can go through, we can construct M as before and go through its columns and find all the unique values that can appear in each column. And those are the possible values that the corresponding pivot can take. We implemented these algorithms in the Julia programming language using rationals to avoid random errors. And we took the representatives for this class from this website. We used our algorithms to confirm the results for order 16, and in all test runs, all of the 34 pivot patterns were generally found within a matter of minutes at most, requiring at most a few 100,000 matrices, which showcases the efficiency of the algorithms and indicates that they are indeed correct, as well as the implementation. The first attempt at recording the pivot patterns of NMR matrices of order 20 appears to have been in the reference you can see below, yielding 1,015 pivot patterns from 3 million matrices. This number was then raised to 1,128, and now we're raising it to 1,246 from so far 3.05 billion matrices. Here you can see all the pivots, all the values that we have found for each pivot. You can see the first one. The last one appears forward to 20, which is the matrices, and then everything else appears to be 2, and 10, which is half the matrix, of the matrices. Here you can see the number of times each pivot pattern has appeared from most to least common. Here you can see all known values for each of the first 8 pivots and for each of the last 8 pivots. And the ones that I didn't mention before, how we have found 36, 118, 89, and 17 values, respectively. Possibilities for future research directions include potentially approaching the problem in a theoretical manner, or improving our algorithms, and extending this approach to work for higher loadings, which is generally very straightforward. That's about it, I guess. Thank you for your time.
Thank the speaker. I have a question already. Understand how difficult it is to solve the problem from 16 to 20. It is well known that NMR matrices are very useful in many areas, like statistics, like numerical linear algebra, and recently in neural networks. And I understand that for the case 20, you have a lower bound for the different pivot patterns. Is it true?
Yes, I mentioned it. That
my question is it possible to have an upper bound?
I don't think I've seen any research regarding that. There are some theoretical results that can be found by using the possible determinants of minors of certain sizes of NMR matrices. And I guess if we take all the possible combinations of the determinants of class 1 matrices, we can probably get an upper bound, but it's probably not very good.
Okay, thank you. Is there any question from the audience?
No.
From online?
Yes, nothing.
No.
No.
We thank again the speaker. And the last speaker for this session is Mr. Nikolaos Koukoudakis from National and Kapodistrian University of Athens. We will talk on learning from the data, how to treat correlated data sets.
Thank you. Ladies and gentlemen, I am Nikolaos Koukoudakis, and today we will talk about learning from the data, how to treat correlated data sets. Now, our main problem for today is this least squares problem. Here we have the X, which is the design matrix, data matrix, as we also call it, which is a n by d+1 matrix. And we also have the regression parameter, which is what we intend to calculate, which is a vector with dimensions 1 and d+1. Now we also include a small noise, epsilon, which we use to check the system stability. So if one method succeeds with epsilon, then that means we can trust this method for other real-time real dataset problems. Let's head on to the state of the art. We have two different paths which we can follow. The first path is the direct method, the minimum norm solution. In this method, we intend to minimize this norm, y minus x vita all squared, and this is a really direct method. Now, for the second path, we use something that's called regularization. There are many techniques to regularize datasets, and one of them is Tikhonov. The Tikhonov regularization uses the parameter lambda, and the LPLQ regularization uses many parameters. However, that includes that we solve a wholly different problem, and that complicates the situation. So our objective is to study the data matrix and study all of its properties so that we can later decide whether regularization is required or not. Now, the first method we initially talk about is the minimum norm solution. We will call it MNS from now on. We will try to minimize this norm, and after many calculations and many applications of linear algebra properties, we come up with this formula on our screens. Using the SVD decomposition, we can calculate this sum, which is more stable than the previous formula. Next, we have the Tikhonov regularization, which is also known as regression. Now we introduce the parameter lambda, which complicates the situation, complicates our problem. Using linear algebra properties, we come up with a very useful formula, and using the SVD decomposition, we simplify it and make it more stable. There are many ways to, this calculates the regression parameter for a given lambda. However, we should compute lambda so that we get the optimal value of vita. There are many ways to compute and to find the optimal value of lambda, and we use the Brent's algorithm. That is because we use the Julia programming language and the respective package for regularization tools. Finally, we have the LP-LQ regularization, which does not use one, but three parameters, P, M, and Q. Now, P and Q must be between 0 and 2, and m is respective to lambda, as we saw it on the previous method. However, here we have three parameters. We need to be very careful on how to choose them, because we need time, and the time that we will use to find those parameters values can be very valuable. Now let's head on to the construction of the design matrix, which we haven't talked about so far. Let's talk about it now. We have the first method out of 4 on total, which is the column correlated covariates. Now, we use a diagonal matrix as a covariance matrix and calculate the values using the normal distribution. And then we can of course compute the correlation coefficient using this formula on the screen. Additionally, we also have a second method for constructing the data matrix. That's called the element correlated covariates, and we start with a square matrix, which has the property that is shown on the screen, and we use that matrix to calculate X. This is the algorithm for the already described method. First, we calculate the values of sigma, and then according to the correlation coefficient R, and then we calculate the values of X using probabilistic methods. Then we have the toy model. Now, this is a different type of construction model, which is simplistic, and that makes it more easy to work with. This simplicity offers us the opportunity to evaluate our conclusions easier. We use this formula to calculate the values of the design matrix, and each column of X is correlated to one another with the correlation coefficient of R squared. Last but not least, we use the spiked covariance model. This is a very interesting model as we construct the covariance matrix as shown on the screen. However, this is a spiked model, so as we see in this example, sigma has 3 eigenvalues. 3 are the 2 of them are just 1, and the other one, lambda 1, comes out as a spike, and that is the evaluation of the name. This is exactly how we construct the data matrix. Now, it's time to examine and it's time to implement what we have already discussed. We use the relative mean square error in order to evaluate which method is more accurate. The algorithm that we use is the following. We calculate first the beta, the regression parameter, which consists of randomly generated numbers from the normal distribution, and then we calculate the y. Now, the beta that we calculated is the exact regression parameter that we want to find. And now we create 100 training sets. For each one of them, we calculate beta, 3 vectors, each for each method, MNS, Tikhonov, and LPLQ. We calculate the relative mean square error, and then we find out which method is the best for each occasion. Let's observe some of the results, which are very intriguing. For starters, in CCC, we can observe that MNS can yield satisfactory results for small r, for example, 0.5 or 0.9. Sigma squared plays small role in this equation. However, as the columns become more highly correlated, MNS is no longer satisfactory, and we need regularization techniques. that can be evaluated and confirmed with the next charts, which we have tested in many methods. For example, we observed ECC, now element covariate, and we always test different and larger potentially dimensions for the data matrix. Here in the toy model, we can also validate that for bigger matrices and larger number of columns, we can see that regularization is no longer needed. For example, in this overdetermined case, we can see that MNS is unsatisfactory, unacceptable for 0.999. However, when we observe the 64 by 1000 data matrix, the MNS is very satisfactory, and any regularization is not proven required. That can also be said about the spikes model for various dimensions, because the MNS proves satisfactory results as the number of columns keeps increasing. We have also confirmed that for the Tikhonov regularization, as we decrease the value of the optimal lambda, the lambda best, we get similar errors as d increases. So for a larger number of columns, we get similar errors. However, if the columns are if the columns are less, which means an overdetermined case, or similar numbers, similar number of columns and rows, then lambda best is clearer. This is a simple diagram of our research, which shows exactly what we have concluded. So in the highly correlated matrices, which means the R is approximately 1, we use the regularization techniques only if the data is not the data matrix is not highly dimensional. However, we can use the MNS, and it is very satisfactory if the data is high dimensional, or if the data is not highly correlated, which means that R is less or equal than 0.9. That means that X is well conditioned. Thank you for your time and your attention.
Yes. Thank you very much for your presentation, your report. Maybe my question will be my question is the following. At the beginning of your presentation, the state of the art section, you talk about 2 different options. Yes?
Yes.
My question is, can we use your result and can we combine benefits of different methods to assure, to provide any more high-level technical characteristics? My question is as a question of engineering to mathematics. Okay? Do you understand my question? Usually we talk if you have 2 options or more options, depending on value of parameters, we can select choice one or other methods, one or other procedure techniques. Yes, but usually there is adaptation approach when we depending on value of parameters can in real time apply both methods, few methods. And so my question is, can you results help to answer my question or to help find more efficient decision?
Yes, I
In
think.
point of view of practice.
Yes, I think that we can always adjust many things in the theoretical background, in our work in mathematical background, and that could mean that we increase the efficiency for our algorithms, and then choose the best method for our approach.
Yes, but I say about possibility apply special solution device to make decision in real time, which methods will be better for your depending on value of parameters.
I don't think I followed.
Sorry?
Sorry, I don't think I followed.
I think we can discuss this point because in collaboration with this one, the important thing is for any real data set, when you want to solve it, can you solve it directly or you need to apply regularization? And this is really very important because in many approaches, most of them they say, oh, the matrix is not square, regularization is needed. Since we have error or since we have noise, apply regularization. But regularization is not so simple because you motivate the problem. You need to think about the value of the regularization parameter, how to apply one parameter to its very complicated. The appropriate choice and with the various of methods of how to choose the regularization parameter. So what we try to do is make the according from the data. Sometimes you can solve it directly, for example, with the minimum of solution, they behave well, and you avoid regularization. So for each data set, study the problem.
I see. Thank you. And now I understand. Yes, but there is other side. If you talk about data set,
Yes.
what I mean, for example, now we have a special request for pattern where we apply two different techniques to build the same, but by using different technique of building two channels, the point of view requirement of all tolerance systems based on narrowness and so on. And in this case, there is very interesting point how we can get different set of data sets or any other techniques which would help to get the same decision, but using different techniques or different parameters of techniques. In this case, we have less value of the risk of common cost failure. I talk about this problem in point of view how get to version is minimal crossing or potential reason for failure. And
Okay, I suggest to continue the discussion with a break. We thank again the speakers, all the speakers. People have a break. There will be a coffee break or not? Or we continue? Yes. Immediately. We continue, okay.
So we have to collect the PDF files and the PowerPoints, and we start immediately.
Το κλείνω. Αλλά είναι το πρώτο αυτό, έτσι. Το πρώτο είναι αυτό. Δηλαδή, μπορεί να το φωνάζουμε Νίκο, δεν πειράζει. Ακούει και στο Νίκο. Και παίρνουμε το Athens. Athens. Number 1. Να βάλουμε όλες τις παρουσίες.